the other primes, contradicting the conjecture, okay. That you had them all. And that's where you prove that a set is infinite, or one of the ways. I mean, another way is to prove that it's equivalent to equivalent meaning bijectively equivalent. You can put it into one-to-one correspondence with a proper subset. So that's a characteristic of infinite sets. It can be put into one-to-one correspondence with a proper subset, such as the set of all natural numbers can be put into one-to-one correspondence with the set of even numbers. Just make n, any natural number n, correspond to 2n. You have a one-to-one correspondence with a proper subset. That makes it infinite. But another way to do it is what we just did, namely assuming that you have all of them, assuming that this set is finite. Well, in that case, you can actually list all of them or indicate a list. You don't actually write them all out, but you could list them all and then show that, nope, that wasn't all, there's always something else. If n is not prime, it has a prime factor, which would have to be one of those primes if those are all the primes. Well, there aren't any others, so that's a prime factor. It's one of those. So do what we did at the top. And then we saw then if n is divisible by some piece of I, which of course is one of the factors of the product of all of them, so it would be a factor of n here and a factor of this term. So that would mean it would have to divide 1 That's a contradiction because p sub I is a prime number, which is more than one. I'll put in I. I can't divide one either because we proved that if a positive number divides another positive number, it's less than or equal to that number. Or the other way to look at it is that one is the smallest number, so the only number that divides it is one, and p sub I being a prime is not one. So again, we got a contradiction. Hence, the hypothesis or conjecture that the number of primes is finite. Here's a word, is untenable. That means you can't have it. So the number of primes is infinite. Then we looked at fundamental theorem of arithmetic. Again, arithmetic referring to the theory of numbers. And it says every integer more than one either is a prime number or can be decomposed, broken down into a product of primes uniquely in exactly one way. Not counting the order, again, you can change the order, but the primes themselves are the same. So for instance, we had 6 equals 2 times 3 or 3 times 2, but those are the same primes. So the decomposition into primes is unique. This is called unique factorization. And so here we have some homework on unique factorization. And those are on the same sheet that had the Diophantine equations. I really think cleaning the screen helped. It's staying steady now instead of jumping around erratically. And the way we did that is to take a number and again, it suffices to look at positive integers because the negative integers are just -1 times a positive integer. Positive integer n can be written in one way. So there are two components to the statement of the fundamental theorem of arithmetic. One is that every number other than a number that's already a prime can be written as a product of primes. And so that's the first part. And secondly, you have to show uniqueness. So in one way, as a product of primes, some books will say that if it's already a prime, then to kind of squeeze it into the same rubric, and they say, well, if it's already a prime, it's a quote product of one prime. Well, okay, it's a slight stretch of terminology. After all, a product indicates multiplication. Multiplication is a binary operation, so you can't really have a product of one number, but you would know what they mean. But I'd rather separate it and be more correct and say it either is a prime, not that it's a product of one prime, or it can be decomposed into a product of primes. What we did is use the theorem that says a number that's not already a prime has the prime factor smaller than the given number. If you couldn't find a prime factor smaller than the given number, then the given number would already be a prime. If it's not a prime, if it's a composite number, then by definition, it has a prime factor, and that prime factor would be smaller. If the only way to factor that number were itself, so it didn't have a smaller factor, then that number would be a prime. And So applying that statement, that theorem, repeatedly gives you a succession, one after another, of, let me emphasize, ever smaller prime factors. And so eventually, as in Fermat's method of infinite descent, eventually you get to a factor of the original number that can't be further factored into smaller factors because there are only a finite number of positive integers less than the original number. The number that's being factored and of course that last factor, which cannot be factored further, is what? It's a prime. If it can't be factored further. So we can factor any number in any positive number more than one, any integer greater than one. It can be factored in at least one way. So a typical way of proving uniqueness, especially when you have an infinite number of possibilities, is to assume the opposite and do it by contradiction. Suppose not. Suppose, say, the number we're factoring is a product of m primes and also a product of R primes with one of them, or say with M greater than R, to allow for the possibility that maybe you can factor this N into a product of M primes in one way, but M also equals a product of a different number of primes, say R primes. Sorry, this is a Q. Okay, then to establish this, we use a theorem that I asked you to prove.
Dr. Freeland?
Yeah.
So M is strictly greater than R because we factor one of those P's, correct? In other words, as we're continually factoring, we get in one less prime number from our P1 to Pm, correct? Is that why P is strictly greater than R?
No, this is a supposition. So we already showed that you can factor N, capital N, in one way, by successive factorizations. It's what we did Thursday. We took 84 and we said, okay, 84 has a prime factor, say 7 times 12. Okay, so it has that's from the theorem that we proved the week before last, I guess, that every integer greater than 1 either is a prime or has a prime factor. Okay, so we look at 84 and we say, okay, well, you think of 7 as a prime factor, but so you have the 7 there, you leave it, and now we look at the 12 and we say, okay, well, 12 is not a prime, it has a prime factor, say 2, and the complementary factor is 6. Now so far we have 84 equals 7 times 2, but we look at the 6 and we see it's not a prime, so it can be factored further into, I know I shouldn't be moving it this way, but I'll do it a little bit. So we have 7 times 2 times, let's take a 3 out of the 6, and the complementary factor is 2. And then we look at that last factor, 2, and we see that it can't be factored any further, and so that gives us a prime decomposition of 84. So that proves that we can do it in one way, but that itself doesn't preclude the possibility that maybe there's another factorization of 84 that's different from 7 times 2 times 3 times 2. And if there is, maybe 84 can be factored into a product of a different number of primes with different prime factors. So what I'm doing here when I'm showing uniqueness is I'm suppose it's not unique. Okay, suppose there are 2 ways, and if there are more than 2, there are certainly 2. So suppose there are 2 ways of writing this capital N as a product of primes, but there's no guarantee that, possibly, as I just said, possibly there's one way to factor N into a product of prime of a certain number of primes, say M of them, and maybe there's another way of factoring that same N into a potentially different number of primes. So if the first factorization has M primes up to P sub M, and the second factorization has R primes up to Q sub R, so if they're different, then, I mean, you can make it equal, greater than or equal to. So a priori, you don't know, maybe, maybe M is equal to R. So you can put that in if you want, M greater than or equal to R, or maybe M is more than R. Or, one of them, either they have the same number of factors, either M is the same as R, or one of them is more. If one of them is more, as we say, without loss of generality, suppose it's M, just because I have it written first, then it's easier to look at. If not, if R is bigger, switch the order just for uniformity. So then R would be greater than or equal to M. Yeah, that's all I'm saying. I'm just saying, suppose you have two prime decompositions, not necessarily, perhaps with the same number of primes. Maybe you can factor 84 into a product of 4 primes, the way we had just above that, 7 times 2 times 3 times 2. And maybe there's another factorization. This is particular for integers. If you allowed your factors to be fractions, you could factor 2 into 1 times 2, or 2 thirds times 6 halves. You could get, or you could break it up into more factors. So when you talk about factorization, you have to know the domain you're in. I think I once showed you that over the field of complex numbers, you can factor a squared plus b squared into 2 factors over the complex numbers, a plus bi times a minus bi. But in real numbers, you can't factor a sum of 2 squares. You can factor a difference of 2 squares. So this is a specific characteristic of the integers, which is why it's part of the fundamental theorem of arithmetic, which is the study of the integers. So again, if this
also, so when you're saying that use theorem, are we using the fundamental theorem of arithmetic right there?
No, I'm proving it. I'm reviewing the proof of it because I want to lead into the homework that I left you with Thursday and make sure you were able to do it. So I'm doing it more quickly than we did it, but and purposely using different words so you hopefully understand something this important. The fundamental theorem of arithmetic, which distinguishes it from other ordinary numbers that you know about, although I did mention that in abstract algebra there's a whole area of study called unique factorization domains, where you have unique factorization. So we're going to use the theorem that says that if a prime divides a product of primes, it actually equals one of those primes. So P sub 1, P sub 2, etc., through P sub m equals Q sub 1, Q sub 2 through Q sub r. I don't know what subscripts I used Thursday, but it doesn't matter. Shows that look at this P sub 1. It's P sub 1 times something equaling the product of the Q's. And that's the definition of divisibility. If P sub 1 times something equals something. That's the definition of P sub 1 divides Q sub 1, Q sub 2 through Q sub R. Semicolon. The theorem, which I asked you to prove, which I'll go over with you presently, which means shortly. The theorem says that P sub R I'll underline equal again. P sub 1 must equal one of the primes Q sub 1, Q sub 2, Q sub R. And again, without loss of generality, just for convenience of notation, I mean, I could be fancy and say, okay, so P sub 1 divides Q sub I, for instance, and then say that therefore since P sub 1 equals Q sub I, we could cancel the P sub 1 on the left and cancel the Q sub I and be left with P sub 2 times, etc., up to P sub n equals, and we've canceled the Q sub I, so it would look like the product Q sub 1 times Q sub 2 times Q sub I minus 1, and then I've canceled the Q sub I, so that's out, and then times the next factor would be Q sub I plus 1, times, up to Q sub R. But without loss of generality, just, I don't know, move. The theorem says that P sub 1, which divides a product of primes, the Q's, has to equal one of them. Move it over into the first place and just call it Q sub 1. So it must equal one of the primes, say Q sub 1. And then from the cancellation law that we proved, so you can get rid of them. So now you're down to just P sub 2, etc., times P sub m equals Q sub 2 through times Q sub R. And so now you have P sub 2 there on the left. P sub 2 times something equals the product of the Q's, which are primes. So since P sub 2, right, you have P sub 2 times P sub 3, etc., equaling the product of the Q's, that says P sub 2 divides the product. P sub 2 divides Q sub 2 through Q sub R. Suppose P sub, so therefore from the theorem, which I asked you to prove, therefore P sub 2 equals one of remaining Q's. Suppose it's Q sub 2, cancel. And eventually, you have a finite number of these, so I can say eventually. You've gotten rid of all the Q's. 1-to-1 with the p's. And since m was bigger than r, or may have been equal to it, the product of any remaining p's, which you'll have if the number of p's is greater than r, well, what happens when you cancel all the q's?
It's going to be equal to 1.
Yeah.
And that's our contradiction, correct?
Well, okay, yeah, you could look at it as a contradiction. Okay, so, okay, I'll put it that way. So those excess factors of P yeah, so you have, whatever P sub, after you've canceled each of the Q's, and so you have if M is more than R, you have an excess number of P's, and so what can you say? If the product equals 1, remember we're dealing just with integers, so if a product of, well, so-called supposed primes, that would be a contradiction, or if any numbers equals 1, what does each of those numbers have to equal? If I tell you A times B times C times D equals 1, and A, B, C, and D are positive integers, what do they all have to be?
It has to be 1, but 1 is
Yeah,
not
they
a
have to be
prime.
1. Yeah, they have to be 1. Must actually be 1. Showing so 1 is not a prime, showing that the actual primes, because those extra numbers that we thought were primes, they're not, they're just 1s. So the actual separate primes in both factorizations the P's and the Q's are of equal number. So up here under the word uniqueness, where it says M is greater than or equal to R, no, it's not greater than R, it's equal to R, right under the underlined word uniqueness. So if we assume that there were more P's than Q's, well, no, after we've canceled 1 for 1, the remaining P's, again, you can either say it's a contradiction of there being primes, or you can just say they're 1s, which are harmless. So the actual primes in both factorizations, the P's and the Q's, are of equal number and actually equal to each other. One for one. The P's with the Q's. That is what we were trying to prove. The prime decompositions, the prime factorizations are the same. So, yeah, so positive integer either is a prime or it is a product of primes in exactly one way. And so when we factored 84 into 7 times 2 times 3 times 2, if that were, say, given on a test, factor 84 into primes, ordinarily, as I've said, if you do something unexpected, I have to look at it and see whether it's right. But if that were a question, of course, it won't be anything that simple. But I wouldn't have to look any further. I wouldn't have to try to figure out what you may have done that I wasn't expecting. If you gave any factorization other than factorization of 84 into a 7 and a 3 and 2 2s, I wouldn't have to look any further. It would have to be wrong. The representation is unique. And again, so this, let me actually write this. And that's essentially why, what I'm going to write now is essentially why this is called the fundamental theorem of arithmetic. Thus, the prime numbers are the building blocks they build multiplicatively as primes, the building blocks of the integers and hence, since the rational numbers are defined in terms of integers, and eventually, the real, and since complex numbers are defined in terms of real numbers, the real and complex numbers. So, yeah, that's important. But what about that? What about the theorem we use to do that? If a prime number divides a product of prime numbers, doesn't just divide them, it actually equals 1. What about that? And again, as usual, if it divides more than 1, which it could, for instance, if 2 divides 2 times 2 times 2 times 2, well, it divides more than one of them. or if 2 divides 2 times 2 times 3 times 5, it divides more than one of them. But if it divides more than one of them, if it divides or equals more than one of them, it certainly divides, or in this case, actually equals one of them, right? So if prime P divides the product of primes, I'm contending that it equals one of those primes. If it equals more than one of those primes, that's fine, but it equals one. I asked you to review the proof of this. The theorem that says that if a number, again, that means an integer, divides a product of two numbers, and is prime to one of those factors, one of those numbers, it divides the other. If C divides AB, and remember this notation for the greatest common divisor? Greatest common divisor, say between C and A is 1, then C has to divide the other number. Remember how to prove that? Remember the theorem that says that the greatest common divisor of two numbers, in this case, that greatest common divisor is 1, is the smallest number that can be written as a linear combination, say AX plus B plus CY, C, equals 1, because the greatest common divisor, suppose the greatest common divisor between A and C is 1. That means that that greatest common divisor, which is 1, is the least integer that can be expressed as a linear combination of A and C. And since 1 is the least integer, there's no smaller one that it can be. And so we have this, it's actually a Diophantine equation. And then what did we do? We multiplied by B, so we got ABX plus, put the B first, BCY equals B, and so we have ABX, but by hypothesis, C divides AB, so it divides ABX. And of course, C divides that because it has a factor of C. What does it mean to say C divides it? It means that BCY, can be written as C times something. Well, yeah, BCY is C times something, namely BY. And since C divides both terms on the left, you can pull out the common factor of C, and so C divides B. So if over here C divides a product and C is prime to one of the factors, say A, then we see that C has to divide the other one. C has to divide B. So as a corollary to that, or a specific case, if, say, the prime P divides the product of two primes, say, P sub 1 and P sub 2, then P has to divide 1. That's the theorem. We have the theorem. One you can put in the word the there. The theorem. We had theorem, the theorem. So the corollary of that theorem is that if P divides P sub 1 times P sub 2, where the P's are all, the P sub 1, P sub 2, they're all primes, then P sub 1 divides, then P divides P sub 1, or, so over here, if it's prime to one factor, it divides the other if it divides a product, or P divides P sub 2. Well,
Dr. Friedman, and because all the P's are primes, this is an exclusive R, correct?
this is what? What was the word after? This is what?
So because P sub 1, P sub 2 are all primes, it is the case that P divides P sub 1 or P divides P sub 2 exclusively, correct? It's not both, correct?
No, it could be both. No,
okay.
You know, if 2 divides 2 times 2, then 2 divides both. 2 does divide 2 times 2, and it divides both. No, but it divides at least one of them. If it divides 2 of them, it divides one of them.
Okay, so this is an inclusive R, or.
Yes. Yeah, you know, in mathematics, unless otherwise specified, it's the inclusive or. In other words, if I say, you know, C divides A or B, there's an understood parentheses or both. Because if it divides one, it definitely divides. If it divides both of them, it definitely divides both. Wait, if it divides both of them, it definitely divides one of them. You know, if I say, do you have $1? And in fact, you have $2. The answer to that question is, yeah, you do have $1. You have another $1, but you do have $1. From a mathematical point of view, from a practical point of view, if you need exactly $1 bill for, you know, some sort of, you know, automated machine, or for, I don't know, I guess bus fares are more than $1, but, and if you have a $2 bill, well, you might not be able to use that, or you might be able to use it and waste $1. But yeah, so in mathematics, if we say that something is true for one thing and it's true for more than one thing, well, if it's true for more than one thing, it's certainly true for one thing. So yeah, the inclusive or. Yeah, otherwise you have to say, but not both. Or you have to say exactly one. But if you say there's one, well, if there's more than one, for instance, there is an integer between 1 and 10. There is one integer. There's more than one integer, but there is one integer. There is an integer between 1 and 10. So yeah, that's how it's used in mathematics. So if P divides P sub 1, well, P sub 1 being a prime doesn't have a lot of choices for divisors. But since P is a prime, it's not 1, because 1 is excluded from being a prime. I should say something about that. I've said it before, but it would be good to repeat now. So if P divides P sub 1, then, well, P sub 1 is a prime, so its only factors are itself, P sub 1 and 1. And so since P is a prime, it's not 1. And so P divides P sub 1. So the only divisors of P sub 1 are 1 and P sub 1 itself, and it's not 1, so it's P sub 1 itself. So P equals P sub 1. If P does not divide P sub 1, then it's prime to it. That is, P sub P is prime to P sub 1. Again, because if P sub 1 doesn't divide, if P doesn't divide P sub 1, what else can divide P sub 1? Well, nothing else. And so P is prime to P sub 1. So P must, from the theorem, this theorem that we just actually reproved, so P must divide the other factor, P sub 2, and by the same reasoning, P sub 1 must actually equal P sub 2. So again, just to recapitulate, if P divides P sub 1, there aren't a lot of choices that P sub 1 has for divisor. It's only itself and 1. And if it's not 1, P is not 1. So if P divides P sub 1, the only other possibility is that P equals P sub 1. If P does not divide P sub 1, then it has to divide the other factor by the theorem that we kind of just reproved. And so the same reasoning shows that, okay, so now P sub 1, P divides P sub 2. Well, P sub 2 is a prime. Doesn't have a lot of choices for factors. The only factors, the only things that are divided are 1 and P sub 2 itself. And so if P divides P sub 2 and it's not 1, then guess what it has to be? It has to be P sub 2. So we've just shown that if a prime P divides a product of two primes, then that prime divides one of the factors or the other factor. And so we can extend this by mathematical induction and say if a prime number P divides a product of not just 2, but of n primes, it, meaning P, equals 1, and again, yes, that means at least 1 of those primes. What primes? The primes in the product. So what I'm saying is, if P divides P sub 1 times the product P sub 1 times P sub 2 times ... P sub, say, there are n of them, then P equals 1, and again, at least 1, of P sub 1, P sub 2, comma, through P sub n. Okay, I mean, I hope you did this. It's a very simple exercise in mathematical induction. We've had much harder ones, which we still haven't completely gone over. I don't know if we'll get a chance to. It's already 7 o'clock. So looks as if we're not getting, I'll just introduce. I thought it was useful to recapitulate some of this, re-explain it, because it is really foundational. And as I said, I want to say one more thing about unique factorization. And also, I want you to concentrate, I've said this before, concentrate on what's really happening, and the notation, requires some care. What I wanted to do today, which I guess will be deferred till Thursday, is to talk about numbers in different bases, and then we'll get to the Euclidean algorithm for finding a greatest common divisor. We know something about greatest common divisors. We just use it in the reproof of that theorem. But how do you actually find the greatest common divisor between two numbers? Well, we'll take a look at that. And it involves a lot of notation with subscripts, but I don't need to get lost in the notation and the details of the subscripts. I want you to see what's actually happening. Then you can compose a proof with the subscripts, as long as you know what's happening. So, as I've said, when you're doing an inductive proof, you can start anywhere and then just show that you can step it up from there, from the case where n equals k to the case where n equals k plus 1. So we just proved the statement true when n equals 2. Namely, we just proved, that's a colon, we just proved that if a prime P divides a product of 2 primes. So I'm starting with n equals 2. We just proved that. Again, you can't have a product of 1 prime. I mean, if you want to, you could say if P divides P sub 1, then P equals P sub 1. That's trivial. Then, in fact, P divides 1, again, at least 1 of, well, more than divides, equals, does divide, but because these are primes, you get actual equality. So we want to, in this extension by induction, want to show that if a prime divides a product of n primes, then it actually equals one of those primes. So there. So we just proved it for the case where n equals 2. Then P equals one of those primes, one of P sub 1 or P sub 2, or both. And now we go to the inductive hypothesis, the inductive assumption, in which we assume or suppose the statement is true when n equals k. So what does that mean? We're assuming that if prime p divides a product of k primes, that's a division sign, assume that if, again, all these p's, I'm not going to keep rewriting it, p and p sub 1 through p sub k, those are all primes, that if p divides this product of primes, then p equals, say, p sub I, which is one of the primes, let me emphasize, one of the k primes.
We also have to change the line where you wrote then p is equal to p sub I. We should change to p sub k, correct?
No. P equals p sub I, which is one of the k primes, p sub 1 through p sub k. And that's what we're trying to prove, that if a prime divides a product, it equals, that prime p equals one of those primes. No, it needn't be p sub k. It needn't be the last one. It's just one of them. So that's the inductive assumption, that if p divides a product of, say, of k primes, then p divides, if you don't like that notation, just ignore it. Just say it equals one of those k primes. I mean, it equals p sub I, which is,
it makes sense now.
Yeah, one of those, one of the k primes. Oh, good. Okay. Well, again, thank you for asking a question to clarify something. Anyway, let's conclude this proof and end somewhat on time. Although I thought I might stop and make a quick comment at the end. So the statement says that if you divide a product of n primes, up here it's underlined, if a prime divides a product of n primes, it equals one of those primes. And so suppose it's true when n equals k. Now prove that it's true when n equals k plus 1. That is, prove that if prime p divides a product of k plus 1 primes, then that prime p equals one of, at least one of those k plus 1 primes. So here's a typical way of doing it. So there we have prime p dividing a product of k plus 1 primes. Show that p not only divides but equals one, at least one. Okay, so when you when you go into the step, the third step in the mathematical induction, so you prove that it's true when n equals 1, or in this case 2, or wherever you're starting. Then you assume that the same statement is true. Let me emphasize, you're not assuming n equals k. You're assuming that the statement is true when n equals k. I've seen repeatedly students will write as the inductive assumption, they'll say, assume n equals k. No, you're not assuming n equals k. You're assuming the statement that you're trying to prove is true when n equals k. And now we have to show that the statement that we're trying to prove is true when n equals k plus 1. Again, the statement we're trying to prove is that if a prime divides a product of n primes, then it equals one of the primes. And now we want to show that that is true when n equals k plus 1. So again, you have to get the inductive assumption into play. The inductive assumption says that if a prime divides a product of k primes, then it equals one of those primes. So let's rewrite that product in terms of a product of k primes. So write P divides P sub 1. And before we get to P sub k plus 1, we get to P sub k times, and I'm putting in parentheses to emphasize this, times P sub k plus 1. Do you agree by the associative property that the way I've written it is the same as that? We have P dividing a product of k plus 1 primes, but okay, so now we have prime P dividing a product of the two numbers P sub 1 times P sub k, and this is a number. Remember at the beginning of the term we talked about closure, and the product of numbers is again a number by closure under multiplication. I'll put this in parentheses, I don't need it, but to emphasize it. And P sub k plus 1. So, look at that. This is not difficult. It's obvious, but you might not think of it this way. So if you break it up this way, you have P dividing a product of one number and another number. The first number is whatever P sub 1 times dot, 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 times P sub k is, and the other number is P sub k plus 1. Okay. From the preceding theorem just above, which says if a prime divides a product, it divides one of the factors, Okay, well, if P divides one of the factors, P sub k plus 1, then as we saw, P equals P sub k plus 1. Again, if a prime divides a prime, the prime being divided doesn't have a lot of choices for divisors. It's just itself and 1, but P isn't 1, so P equals k plus 1. But if P does not divide P sub k plus 1, P must divide the other factor. P sub 1 through P sub k, but the inductive assumption, inductive hypothesis, the inductive assumption says that if prime P divides a product of k primes, it equals one of the primes. So in either case, P divides or equals